If player 1 doesn't know what player 2's payoffs will be depending on how the game is played, then we will say that player 1 has incomplete information about the game. In section A of the chapter, all of our games were complete information games. Each player knew what every other player's payoffs in the game would be. We'll now begin to consider incomplete information games. Consider, for instance, the payoff matrix of a simultaneous move complete information game in which player 1 can go up or down and player 2 can go left or right. Suppose player 1 knows his own payoffs, and he thinks player 2's payoffs might be as described in this payoff matrix. If he's right about player 2, then he knows player 2 has a dominant strategy to always go right. If player 1 goes up, player 2 does better by going right because he gets 15 rather than 10. If player 1 goes down, player 2 also does better by going right because that gives him 5 rather than 0. Given that player 2 in this case has a dominant strategy of going right, player 1's best response is to go down, and so the Nash equilibrium in this game is for player 1 to go down and for player 2 to go right. But suppose player 1 thinks there's a chance that player 2's payoffs for going right are different than those we've just analyzed. In particular, suppose that player 1 thinks there's a chance that he might be playing a player 2 where the payoff matrix describing the game is the one that appears on the right. This payoff matrix is identical to the one on the left, except that we've changed the payoffs for player 2 for going right. And now it's a dominant strategy for player 2 to go left. If it's a dominant strategy for player 2 to go left, player 1's best response is to go up. So the pure strategy Nash equilibrium in this game is for player 1 to go up and for player 2 to go left. Any incomplete information game can be modeled as a sequential game in which a non-strategic player called nature starts the game by assigning types to individuals. Here, for instance, nature assigns player 2 the type on the left of the picture with probability rho, and the type on the right of the picture with probability 1 minus rho. After nature has moved, we will assume that each player knows his or her own type, but uninformed players only know the probability distribution used by nature to assign types. Player 1 then does not begin the game at a single information node. Rather, he begins the game from an information set that contains 2 nodes, and he thinks that he's on the left node with probability rho and on the right node with probability 1 minus rho. Put differently, when the simultaneous move game begins, player 1 thinks that there's a probability rho that he's encountering a player 2 of the type depicted in the payoff matrix on the left side, and he's encountering a player 2 of the type that's depicted in the payoff matrix on the right side with probability 1 minus rho. If player 1 knew that he was playing a player of the type in the lower left payoff matrix, he would know that he's playing a player whose dominant strategy is to always go right, and therefore his best response would be to go down. Following nature's move, player 2 would know her own type and would therefore know that she's the type of player 2 that in fact is playing the game depicted in the payoff matrix on the lower left corner. Since the 2 players are playing simultaneously, she would not observe what player 1 has done, and would therefore not know whether player 1 has gone up or down. Thus she is moving from an information set in which she does not know whether player 1 has gone up or down, but she does know her own type. Player 2 then has a choice of moving either left or right, not knowing whether player 1 has moved up or down, but knowing that she's the type of player depicted in the payoff matrix on the lower left corner. The payoffs at the bottom of the tree then appear as they do in the payoff matrix. Beginning with the left node for player 1, we've therefore depicted in the form of a game tree the simultaneous move game we initially depicted in the payoff matrix in the lower left corner. To do this, we've used an information set for player 2 that indicates that player 2 does not know whether player 1 moved up or down when player 2 has to decide on whether to go left or right. In other words, when player 2 reaches her information set in this game, she has no information about the actions of player 1. That's the same as saying that player 2 has to decide on her action simultaneously with player 1. Any simultaneous move game can then be depicted in game tree form, or in what's also known as extensive form, if we employ information sets the way we have here. We haven't mentioned this in section A of the chapter because we've had no need to do this. But here, even though player 1 and player 2 are playing simultaneous move games, we can depict those games in game tree form to fit them into the incomplete information framework where nature is actually the player that moves first. If, on the other hand, player 2 is the other type, the type whose payoffs appear in the lower right payoff matrix, then player 2 will once again know her own type, but she won't know whether player 1 has moved up or down when she has to decide what to do. Thus, her information set will be such that she doesn't know what player 1 has done, but she does know what side of the game tree we're on, whether nature has assigned her the type on the left or the type on the right. We can then finish depicting the simultaneous move game on the right, just as we did on the left, in a game tree form. What makes this a simultaneous game, despite the fact that we're depicting it in game tree form, is that player 2 begins at an information set where she does not know whether player 1 has moved up or down. One reason it's good for us to depict incomplete information games in this way is that it clarifies what it now means for players to have strategies. In any game, a strategy for a player is a complete plan of action prior to the beginning of the game. The game depicted here begins with nature's move. In other words, it begins prior to player 2 finding out what type she's been assigned. Thus, a strategy for player 2 is a plan for what to do in the event that nature assigns her a type 1, whose payoffs are depicted in the payoff matrix on the left, and what to do if nature assigns her a type 2, the payoffs depicted in the payoff matrix on the right. Since there's a dominant strategy for player 2 in each of the simultaneous move games, we know what the strategy will be for player 2 in the incomplete information game. Her strategy will be go right if nature assigns me a type 1, and go left if nature assigns me a type 2. Player 1 knows this, but he doesn't know what type nature will assign to player 2. All he knows is that one type will be assigned with probability rho, and another will be assigned with probability 1 minus rho. Whether player 1's best response is then to go up or down depends on what value rho takes. If it's more likely that player 1 is on the left side of the tree, player 1 will choose down. But if it's more likely that he's on the right side of the tree, he'll choose up.